everyone. Thank you for attending the conference and also attending this talk. I'm going to give like the agenda basically is like, I'm going to divide in like two parts. The first one is like a basic introduction about geospatial data and GIS in general to like make you like familiar with like the terminology and all the words the jargon that we use in GIS. And the second one is I'm going to move to a notebook, and then I'm going to demo what we can do in terms of GIS with duckdb. So that's going to be like the presentation today. So let's get started. And the first thing is like an introduction about what is Geographic Information Systems, or GIS. And basically is location data. Is almost everything that happens somewhere. Basically, it has to be related to location. And GIS are systems that they can help us to like deal with geospatial data. So we can capture data, like for example, you fill a form, they can track you, or you can like send data across your GPS in the cell phone, and then you can store it. That's what we're going to talk about today, which is like geospatial databases. You can edit the locations. Also, you can make analysis of that data and also visualization and display that data. And the focus of this talk is going to be on store, analyze, and displays. This is going to be the focus of the presentation. And this is repeated. Anyway, so what is the data? The data can come in like many forms through various sources. So we can have like paper interviews, mobile phones, like airplanes, or satellites. For the people that are working with like remote sensing, like satellite imagery. And usually we have like spatial data and non-spatial data, which could have like tables. We have like points, lines, and polygons, which is like geometries. And also we have the pixels, like the pixels that we take from the camera. And the way we represent geography, we can have like two main types. The first one is better, like this. Is like discrete objects. So those objects are like well-defined boundaries, are like points, lines, and areas. Those like you can count those like polygons or those geometries, and they are like persistent through time. So for example, administrative boundaries. So usually the admin boundaries, or the way the boundaries are set for the countries, they don't usually change, but sometimes there are like changes, and changes are needed to make them. But they are like persistent through time. And also, they don't represent, like, there are not like changes in values across small distances. So for example, the boundaries of Italy is, they don't represent like the small changes. But if you switch, for example, vegetation temperature, that's a satellite imagery. So the value that you can get in 1 kilometer could be another value in the next following kilometer. That's like, in that case, when you have like discrete objects, those are not considered discrete. Those are like continuous fields. So those fields are like properties that like they change consistently over space. And usually the examples could be like soil moisture, water depth, temperature of the surface, and so on. So these are like the examples, like small examples. This is like an area of like vector data, discrete objects. This is like an area of some like farm. And these are like the most popular, which is like a neighborhood. So you can you can like vectorize, and then you can draw like lines or roads or buildings and so on. And for continuous fields, we have like elevation models, or elevation images, water discharge values, and also as I mentioned, the surface temperature of the Earth. So these are like the main difference between like discrete and objects and continuous objects that we have. So vector data is used to represent like discrete objects. And we have the points, which is locations recorded as coordinates. So as we have like the latitude and the longitude, and those are like individual locations. So you can draw the points, and then you can display them on a map. The lines are like a subset of points. So you can like draw one point, another point, then you can make them together, and then you can create a line. And finally, you have the polygons. So you have the lines, and those lines are close ones. So polygons are considered like line strings, where the first value of the coordinate is the same as the last value of the coordinate. So those are in closed string, and those are considered polygons. And vector data is like spatial data, but the data that we use for vector data consists on two parts. The first one is the geometry itself. So it gives us like the spatial information, the line string, or the polygon, or if it's a point, and so on, and the values in terms of like the coordinates. And they represent the shape of the phenomenon. So in this case, these are like the shapes, and the additional information is called the attributes. So the attributes as like information that is like additional to the geometry. So let's take an example of this one. So we have like these polygons that they represent buildings. So the geometry is like, it says, okay, it's a polygon, and these are the coordinates of the polygon. And the attributes, or they are also considered properties, are like information about the address of the building, the number of the building, the number of floors in the building, the roof type, and so on. So these are like attributes. And then if we combine the geometry with the attributes or the properties, we can create something called a feature. So geospatial data in terms of vector data is like a collection of those features. And then that's the one we manage and then we work with. So not necessarily you can have like only points, slides, and polygons, but you can combine them. You can have like a point or like an array of points, which is a multi-point, or you can have like multi-line strings, or you can have multi-polygons, or also you can have a polygon inside another polygon, which is the polygon with holes that are like shown here. So you can combine them together, and well, these are like considered geometries. For raster, it's different because we represent like continuous fields. As I mentioned, you can have like values that change in small distances, like as I mentioned, the temperature. And this information is like stored in like similar to images because it's like an array of numbers, which is like the pixel, and each pixel represents one value. And you can represent the value can be different types of values. For example, population count, population density, yeah, you name it. But those values, they have like a fixed distance, and each pixel represents one fixed distance. For example, you can have this pixel that represents population number on an area of 100 meters, but you can have also the same value of population number, but the area of the pixel represents 1 kilometer. So you need to like check and track what is the size of the pixel, what does that pixel represent in terms of like area. And there are like changes like vector and raster data. But before I continue, I'm just gonna move to desktop app, which is of QGIS, so we can like see better and to make the difference between vector and that raster data. So I have like here 4 layers. I have the administrative boundaries of Colombia for the admin 0, which is the country itself, admin 1, which is the departments, and admin 2, which is the municipalities. And I also have the population raster. So this is the admin 0. As you can see, this is the admin 1, and this is the admin 2. Yeah. And this is the population raster. So if I want to select one, let me just check this admin 1. And I want to see the attributes, I can just go here. This tool makes it like easier. Oh, let me just make it like this, better. So if I select this one, it will show me, this is like the geometry of this feature. I have this array of, this is a geometry collection, a feature collection. When I select one feature, and then I can see here, you can, I guess, but you can see information about the administrative name, the administrative code, what is the country belonging, and so on. But the attributes for this admin 1 are like different if I select the admin 0. So if I go to admin 0 and then I select it, I have the whole geometry, but I have other types of attributes. So when you manage and you work with geospatial data, make sure that each element in that collection is consistent with all the attributes and geometries. That's ideally. I mean, in theory, you can mix it. You can mix polygons with points and polygons with different geometries, but when you want to work with that, it could be like really complicated. So it's better that you isolate the data using the same geometries and also using the same attributes. I'm working right now with vector data. But when I move to raster, which is over here, this one. So this is the population raster level, and then if I zoom in, the more red it is, the higher the value of the population. And then here you can see like the image gets like pixelated. And each value of each pixel represents the population that I have across that area. And I know that this area is 1 kilometer. So this is the amount of value that I can get in 1 kilometer in that region. Okay? So now, going back to the presentation, the way that you want to work with geospatial data, it like depends on the application that you want to do, or the thing that you want to do. Sometimes vector suits better, sometimes raster suits better. The way you work, the way you share that information also depends. And some vector, they can be like transformation. You can convert vector data to raster, and also you can, and vice versa. Now that we're talking about duckdb, duckdb is like a database for managing data. You can have data as tables, and now we're going on that, but it only supports vector data. That's something that you need to be aware of that. And as I mentioned, you have like when you create a map or you create a web map, it's like an integration of different data sources. You have, as I show you, you have like admin 0, admin 1, and admin 2, and each one goes above the other. And you have like you can create like a combination of those layers or those like tables, and then you can have you can assemble or you can create your own database. So you can have a combination of like each data source. Each one has is a collection that has features, and each feature has the geometry and it has the attribute consistently. And also you can collect and stack them together, and then you have your database. So that's in few words what is like a geospatial database: a collection of features, a collection of layers, where each layer has a fixed array of features. And now we're going to duckdb. So this is the second part, and I have shown you, I just created something called a notebook. Let me see if you can see better. It's better. So this is a notebook, and I'm just going to explain how can we use duckdb to manipulate geospatial data. So as an introduction, duckdb, as I mentioned, is a database where you can like create tables, and then you can manipulate tables. The good thing about it is that it's like different to Postgres. You don't have like an application itself, like a binary that you need to run, and then you can connect through username, password, port, and so on. The thing is that you start from a scratch database or a persistent database, which is a file, and then you start including or removing data. So you start empty, and then you start creating and improving data. So the main goal is how to work with geospatial data inside duckdb. There are many different ways to do it, but I'm going to show you the one that has been like easier for me. And the first thing that you need to do is like, okay, we import duckdb here, and I'm using additional libraries for like displaying data and so on. I'm gonna explain later. So we use duckdb, and then I just create a normal connections. And with this connection, I just start appending the extensions that I need. So I'm just gonna use two. The first one is spatial, so it's the library to manipulate geospatial data or the geometries that we have been talking before. And also the HTTPFS, which is the one that we're going to use to load data remotely. That's the one we're going to use. So remotely doesn't mean like a standard HTTP static site. You can also have like your files in S3 buckets or your data in S3 buckets, and then you can just set up the connection inside duckdb, and then you can retrieve that straight away. So when I run this, you can see that I have just included connections. Include extensions. I install them, and then I load them. And finally, I run this command, which is describe tables. So this table only shows me that I don't have anything, which means that the database is empty. It's an empty database. I don't have anything. I will start right now including data. Okay? So as I mentioned, vector data is spatial data. You have the geometry and you have the attributes. And they represent the shape. And now I'm just going to start creating geometries. So this is the function to create a single point. So this is a query. And as I forgot, duckdb supports works with SQL language. It's a dialect of SQL, and then you can perform queries normally as you can use, similar to Postgres. Not the same to Postgres, to PostGIS, but it's quite similar. So this query basically creates a point. So this is a point, and when you create it and then you run it, you can see that this column is named geom, and the type is going to be a geometry type. Okay? So you need to be aware that this should be, or sorry, this must be a geometry to start operating with geospatial data. And I can continue working on that. So now here I'm just going to apply small operations across the geometries. In this case, I'm just creating a line string here. So, sorry, my mistake. So I have the point here, and what I do is I evaluate the area of the point, the length of the point, and the geometry itself. So these are the results. And the area is 0, the length is 0, and this is the point. But in this case, I just make a line with a length, with an array of points. So this is the line string that I create, and then I just evaluate the same result. So here you can get the query that I create the line string, and here you can get the query to get the area, the length, and the geometry itself. So for this case, the area is going to be 0 because it's a line. The length is going to be the length of the line. In this case is 5, and this is the geometry that I'm using. But if I make a polygon, which is this one, this is the query, the subquery that I use to make the polygon. And the area is going to be the area of the polygon, which is fine. The length is going to be 0 because, I mean, the length of the polygon. And this is the geometry that I'm using. So these are the values that I could get, and these are like the types of operations that I can do inside a query. So the benefit of using SQL is that you can start creating subqueries one after the another. So you can do some sort of analysis, and at the end you will get results, and everything is going to be stored in a single query. So that's like the benefit of like using duckdb compared to normal tools and libraries that are used in geospatial in Python. Because, for example, with Shapely, you need to download the information, and then you need to separate the attributes from the geometry. And then you need to have the geometry as a Shapely object, and then you need to operate and do the things that you need to do, and then you need to go back and then append the attributes. So it's kind of like a complicated, and I'm going to explain you why. Now that I have a CSV file. So this CSV file represents something that we work in WFP. It's called RWI, which stands for Relative Well Index. So I have the latitude and longitude of a point, a location somewhere, and that relative well index indicates the level of wealth that can have in an area of 2.4 kilometers. So I have the point, and I have the area 2.4 kilometers, and this is the value that I can get. Negative means that it's like the wealth is like not good, and positive means that it's good. So the better, the higher, the better. Okay. So this is the data, and this data is stored in a CSV file. I have it here. This is my CSV file, and then if I load it, I can load it straight away in duckdb using this query. So select star from read CSV. The problem with this is that this table right now, the way it is right now, is not geospatial. As you see, it's like a latitude and longitude. Those are like doubles, and those are like numbers. So now we need to like make them geospatial. So what I do is that I can just create the table, create the same table here, but what I do is like I take the longitude and the latitude columns, and then make the point of it. So if I see again and I want to describe the table, you can see that the geometry here is the geom. And let me show. I think I show it here. That's the cool thing of live coding. So here you can see the RWI value, the error. We're not going to use for this presentation, but this is the point that we created before. So I took the two columns, I make a point, and now for duckdb, the tool will understand that it's going to be a geometry itself. And then I can start working with it. So something to talk about before continuing is geospatial formats. So as I mentioned before, data, the vector data, is like classifying two main fields: the geometry and the geometry and the attributes. But that data, the way you serve that information, the way you share that information, or the way you read that information, could be, I mean, you can create a huge JSON when you can have each field, or you can have a CSV file. You can have many ways to serve it. I mean, there are like infinite ways that you can serve that information, right? So there's an organization, it's called the OGC, Open Geospatial Consortium. So what they have like dedicated most of the time is to develop some sort of like a standard or like a structure, or how you need to serve or you need to generate that data, or how you need to read that data. What is the advantage of having like a standard for that interoperability? Which means that, for example, I can have that information as a GeoJSON file, and then I can have it stored somewhere, and then I can use any web map client that can read GeoJSON, and I can just load it. I can just put the URL that I need, and then I can just load it, and then I have my web map beautifully visualized. So I wanted to show that because there are like so many formats that you can work with. I mean, there are like many ways, and that's another advantage of duckdb. So internally, duckdb has it's called the GDAL. So GDAL is like a library to operate geospatial data, and they support many formats. What's the benefit of that? Is because you don't need to think about which is the library. You don't need to think about which library, or you don't need to install the library that, depending on the format that you need to use it, right? So there's a library for shapefiles, there's a library for GeoJSONs, there's a library for GMLs, and so on. So you need to install it, and then you need to operate and do the things that you need to do, parse the data, and so on. With duckdb, it's just a single st-read command. So here, let me show you here, this one. So here I have the URL of a GeoJSON that is showing the same data that I show you here in QGIS. Sorry, yeah. So these are like the boundaries. And then what I'm going to do is I have these boundaries remotely. And the query, what it does is like I just create a table called boundaries, and basically it's just reading from the URL. So it internally checks what is the format, and then parses it automatically, and then creates the table. So I have two URLs, one for URLs for municipalities, which is admin2, and then another URL for admin1. And then I just create the tables, and then I can just see what is the data inside the tables. So this is the case for boundaries, which is the admin2. But if I switch to admin0, yep, this is the admin0, and if I use the admin2, I can see all the attributes that are inside that file. And also, I can see what is the geometry that I have inside that file. So it's like easier to like operate. And now that I have the table, I can start like combining tables. I can start operating, and everything is going to be inside an SQL query. So simple operations of data, I can just filter by an attribute. I can, for example, in this case, I want to totalize the number of admin2s given this column name. So this is the value, and then I just count, and so on. The same for the other table, the RWI table. You see the points and the RWI value. I want to get how many points are below 0, have like -12. So everything is like inside as I mentioned, at the beginning you started with a connection in memory, which was like empty, and then you started including data. And each data is organized on tables, and each table has its own set of attributes and geometries. And then you can, once you have like everything consistent, you can start like combining and making joins and so on. So this is an operation that I do across the attributes. And this is an example for visualizing the data. So here I'm using like, just create a small 2 drop-downs. So one is for the admin2, and the other one's for the admin1. And if I go here, yeah, so this query, what it does is I'm just going to get all the geometries from the boundaries, and I'm centering them a leaflet map. And what I do is once I get the data, I just create a geodata frame of the query that I need. So in this case, I just want to get all the RWI values, the first 5,000, and visualizing the web map. So here, you can see that this is like all the boundaries that get at admin2 level, but also you can see the points for the RWI values, the first 5,000. So the cool thing is that I can just, if I want to change the table, I want to use is admin0, I can just change what is the table that I want to get the data, because I know everything is like standard. and the geometries are standard. I just change it, and I can just show the admin 0 with the same points. But if I want to show only the high ones, RWI higher than 0, limit, I don't know, the first 500, and I run the query, you can see all the points that have that RWI value. So it's operations across the attributes, and now you can also do operations across the geometries, which are called geospatial relations. So you know that you have one table, which is a list of points, and then you have another table, which is a list of polygons, right? So you have the RWI, and then, for example, you want to know what is the amount of points that are inside a given polygon, okay? So in this case, the spatial operation is going to be within. So I'm going to find which are the points that are within a given polygon, right? I have the two tables already in the database, and now what I'm going to do is I'm going to select here in this query. I want to select what is give me the geometry that matches the given admin name, okay? Here, I'm using just to extract the centroid. I just want to center the map where I want. So I take the geometry, and then I just compute the centroid, and then I extract the latitude and longitude. And then I have another query, which extracts the geometry that I want, and then I perform the operation that I need. So here, you can find that this is the operation that I say, okay, I have the geometry of points from the RWI table, and I want to find which are the points are within the boundary that I filter, okay? And once I filter, I'm just gonna get the data, and then plot it on the map. So this is the result that I get. And the cool thing is I made the drop down, so if I'm showing Barranquilla right now, but if I want to select another city, I want, for example, Cartagena, I can show which are the points that are within that polygon. Sorry, which are the points that are within that polygon. And then I can just continue it. It will be like a standard. So move to Medellin, for example, and here you can see it. So that's the way you can like operate at an attribute level. But it depends on the geometries that you use. Also, it depends on the type of analysis that you want to make. You can, be creative. You can find intersection of polygons, union of polygons. You can combine polygons together. You can make a line string given a set of points. So these are like the usual geospatial operations. Yeah, operations, but it depends on what you want or what you need to do. Okay. Continuing, projection. So what happens is that the main problem that we face in GIS is that the world is considered like a three-dimensional spheroid. And when you want to display is a two-dimensional plane, canvas, right? So the way you represent or the way you transform that information, you will have some sort of loss or the information will be like distorted. The best example is the Antarctica. So in the south, imagine that you take the world and then you unroll it and then you put it in a canvas, and then inside that canvas you see that the Antarctica is like stretched. So it's stretching the higher latitudes and in the lowest and the highest latitudes, and then you will see like the data distorted. But that's a way that you represent the data, because instead of that, you can rotate the world, and then you can just show the plane or the way you visualize it, centering the information in the Antarctica. In that way, that information is going to be visualized in that way, so the data is going to be better for that location. But for globally, everything's going to be like around points. So that's a problem that we usually face. And also, each way you represent the information, it will have its own measurement units. So for example, this projection, which is WGS84, the values or the metrics that are used are degrees. But when you use another one, like the Google projection, they use like pixels. And there are some other projections that they use like units in meters. So it depends. It depends on what you want to do. It depends also on the extent of the data that you want to use. If you want to globally or you want to center across a country or across a region, you can need to reproject or not. So let me show you an example that I have. The end goal that we have is I want to know which is the total population that is that has like low wealth. in a given city. That's the end goal that I want to do, and I want to use I want to play with operations to do that. So, as you see, the query gets more bigger. So, what you do is, okay, this query, what it does, I want to find the squares, or I want to create squares that represent area 2.4 kilometers. So the first thing that I need to do is to find the wealth values negative for a given city. And then from those points, I will create a buffer that is going to be a square, and that square is going to have 2.4 kilometer area. The problem is that the projection of the points are degrees, and the other ones and the ones that I need, the value that I need to create the buffer is in meters. So what I'm going to do is just reproject to 1, then create the buffer, and then go back to the previous projection. So this is the query. As it gets a bit complex. So here I do the transformation, then I create the buffer up here, and then I can go back here. So I make sure everything is in a single query, and then once I get that, I will get the extracted geometry. And then I just plot it here on the map. So here's the example of Medellin. So here you can see which are the areas where the wealth index is lower. It's below than 0. Because I applied the filter here. The RWI is higher than 0. Sorry, it's lower than 0. So this is the way, but I can change it if I need to. And if I switch city, for example, Barranquilla, you can see these are the areas where the wealth index is low, below 0. So yes, now I have the areas. And now I need to pass the population information, because I know the areas and I know how to pass the population information. But that information is a raster, okay? Because we were playing with vector data and we don't have rasters, right? duckdb doesn't work with rasters, and the population is a raster. The operation that we need to do is called zonal statistics, and this is a small diagram, which what we do is, okay, we have the location of the boundary, and then we just overlay the boundary with the pixels of the raster, and then we select the values of those pixels that intersect the boundary, and then we just compute statistics. So we can compute count the number of pixels, we can count what is the maximum value of the pixel, we can count the sum of the pixel we totalize, we can compute the statistics that we need to, right? So for this case, we need to totalize. But we cannot work straight away in duckdb. So there's a big problem. However, there is a solution. Python has a tool to work with rasters, and then you can compute zonal statistics. But the advantage of duckdb is that when you don't have a function that does what you need to do, you can just create a Python function when you pass some sort of parameters, and you can inject that function into duckdb. And once you inject it, you can call that function, and you pass those parameters, and then it will run inside, and then will return the value that you need. So that's a huge advantage, because whatever we don't have inside duckdb, we can just create a custom function, and then just use it. So for this example, I'm just going to use a library called rasterstats, which has this function. And this is the zonal stats function, zonal stats logic that it does. So this is the function that I create. I just pass a list of geometries, which is the squares that I showed you before, the squares for a given city. And I pass the path of the file of the raster that I showed you in QGIS. So I do it there, and then I compute the function that I need, and then I just totalize. So what I do is, okay, for each square, I'm just going to get the sum of the pixels of the population for each one, and then I just sum everything. And that's the value that I'm going to return. So this is the information that I get, and then I just show you, this is the whole complicated query that I showed you before, but what you need to be aware is that this line is the line that I say, okay, duckdb, this is the function that I'm going to create, this is the one that I'm going to name it, and this is the function I'm going to use. And then, once I know it, I can just pass it here. So this is the function that I created, the custom function. I just pass the geometries that I received from the subquery, and then the path of the raster that I have locally in my computer. So in this way, I can just run a custom function in Python as a SQL command, as a custom SQL function. And so on, I can just run it, and I can get the result that I want. So for example, I have the drop-down before, and the city is Barranquilla, but if I want to switch for Medellin, you will see the value of the total population. So all the squares were like computed and everything was done and recomputed and so on. So yes, that's a big advantage that we use in duckdb. And to finalize, because I have 5 minutes left, how do we apply this inside WFP? This is like a brief demo of an application we call Prism. So Prism basically is a tool for like monitoring hazards and emergencies. And one of the features is that we have like tropical storm data. So tropical storm data basically is like a big polygon, which when each polygon represents like a wind buffer. And we have here the locations of the points where the storm is going around. So we have the data source, and each 6 hours, there's like a source. They are like emitting like a report of where the storm is passing through. So it's like a big GeoJSON. We just grab it, we parse it, and then we just show it here on the map. The thing is, once the storm makes like a landfall, I mean, there's like a forecast of a landfall of a storm, as shown here, we can do additional analysis. So we take the landfall, we can compute where is the landfall of the storm, at what time the storm could fall. If we have the storm, what is the wind speed values across that, and we create buffers, and so on. We can just synchronize with the administrative boundaries to know which are the districts affected. So it's like a mix of geospatial operations when you overlay things, and then you can just have those, that's like table of like the district with the number of people affected by so on. So this is like an application. And also the advantage of duckdb is that as it is like a wrap, it's not like a wrapper of a library in C++. It's like a tool that is like compile itself in Python. You can just install it, which can take like seconds, like 5 to 10 seconds. And then you can just run it as a Lambda. So we have a Lambda running, checking for new events. And then once it's done, we just run a duckdb query that creates the data and store it as a GeoJSON. And then we serve it over S3. And then we just fetch here in the dashboard. We can just visualize that data from S3. So hope it's clear. And thank you. That's
Thank you, Jorge, for the wonderful presentation, and finished actually almost 2 minutes early. So yeah, we have times for questions. I recall it's pycon.it/Slido. We already have a number of questions. And let's start with the first one. And if you want to raise your hand, if you have asked the question so that the speaker looks at you when he answers that, feel free to do that. The first question is, what's the advantage over GeoPandas?
So GeoPandas uses internally the GDAL library. So in order to compile GeoPandas, you need to have GDAL installed. So installing GDAL sometimes it's like a bit complicated. It's not like quite easy. And duckdb, when you install it, it has already the GDAL driver integrated. So you don't need to worry. You just need to load the extension straight away. That's the main difference.
Thank you. What are some good starting points to find geospatial data that I can experiment with?
It depends on the application that you want to use or the thing that you want to use. I mean, for the humanitarian sector, the most common is the HDX, the Humanitarian Data Exchange. So this is like a repository where people can like download geospatial data if they want as a shapefile and so on. But there's another one, which is OpenStreetMap. The thing is that OpenStreetMap has a different data structure to manage geospatial data. So it could be like a bit complicated to work with, but duckdb has support for read OSM data.
Okay. Thank you. What are some good starting points? Already. Is there support for binary formats such as GeoParquet? Is it a format you recommend, or do you prefer to use GeoJSON?
That's a good question. So GeoJSON, I forgot to show that. So the way that you display the GeoJSON data is this way, which is this one. So all the attributes are stored in a field called properties, and the geometry is stored in this way. So it's a big JSON. And when the JSON becomes like really, when the data that you want to manage is like really big, for example, admin 2 level of a country is at a global level, is going to be like a huge GeoJSON. GeoParquet has the advantage that you can do Hive partitioning. So you can partition the data the way you need, and everything is going to be stored in folders. So depends on what you want to do, but for global data, it's better to use GeoParquet. And also there's like flat GeoBuff, which is the data is also indexed internally, so you can use it also. It could work.
Thank you. How can you embed what we have seen in a web app? For example, how did you do it in the Prism app?
Can you repeat the question?
How can you embed what we have seen in a web app? For example, how did you do that in the Prism app?
Okay, so as I mentioned before, we had a script, a Lambda function that is checking for new events, for new storms arriving. So once the storm arrives, we receive the information, we check for if there's a landfall or not, and then the analysis output, we store it in an S3 bucket. So we have the Prism app, and the Prism app, what it's doing is reading straight away the bucket from the bucket, and it's basically a GeoJSON output files. And then we don't need to parse it, we just need to fetch and load straight away.
Okay, I think we have a few more minutes. It's 25, right? Will you be sharing slides and notebook, maybe on Discord?
Sure.
Another question. Why there is a single geometry type instead of 3 different types for points, lines, and polygons?
That's a good question. So for duckdb, duckdb enabled the spatial extension, the spatial functions, and they only consider everything as a geometry. That's good and bad at the same time. Good in terms of since everything is a geometry, you can just operate over geometries and find the query. You don't need to worry about consistency and so on. The bad thing is that sometimes you don't know what you are reading or what you're inserting, what type of geometry you're working on. That's the main difference with, for example, PostGIS, because PostGIS, you can create a column that is a geometry, and you can force what is the type of the geometry that you're going to use, and also the projection that you want to use, the spatial reference system. So sometimes if you have a table of points and you want to insert a line, Post will say, no, I won't do it. But for duckdb, yes. Maybe in the future, I don't know, for the duckdb developers will force that, but it would be sometimes good for some occasions.
Okay. What notebook app are you using?
That's a good question. So I'm using called Marimo, Marimo Python. Not sure if someone is have heard of it. So it's like a new version of Python notebooks. And the main difference is when you make a change in one cell, it can affect the down ones. So that's a better reactivity. So when you want to create dashboards and you want to do things, Marimo is quite good. So yeah.
Thank you.
That's the one.
Yeah. What's the overhead of using Python functions in duckdb? Getting technical.
I haven't tested. Honestly, I haven't tested yet. But what happens is that when you create a function, the function goes to Python, goes to Python domain, performs the computation that needs to be done, and then goes back to duckdb. Not sure how fast it would be, but I don't have the answer, honestly.
Mm-hmm. And still on this is how do you debug the queries with an injected function?
How to debug? I'm using prints.
As don't we all?
I'm using.
Can I integrate duckdb with multispectral data, like the ones from Copernicus Sentinel? Should I also use libraries like RioXarray, etc., or duckdb can manage this data?
I think Copernicus data is raster level, so raster level is not easy to work with duckdb. You need to have custom functions to operate with raster. But if you use duckdb, you can just create custom functions that call the raster library and then do what you need to do there.
Okay, last one. Is there a way to use duckdb and spatial library writing actual Python syntax instead of SQL-like?
I think not. I think duckdb duckdb accepts only SQL queries. If they have a special dialect to run queries in SQL. But there is another library called SQL-glut. Not sure if people are aware of this. So SQL-glut, what it does is imagine that each subquery that I do is considered an object. You have an object, and then you can just create a tree of objects when you can connect one object to the tree and then, or another object to the previous one, and then you can just make, and then everything, once it's done, the tree is parsed and then transformed into an SQL query. So internally, it's going to, I mean, at the end, it's going to be an SQL query, but everything is going to be created dynamically as an object. So for APIs and everything, it's quite good.
Thank you for the excellent talk and for the answering a lot of the questions.